All right, so what we're going to look at today is the Arps decline curve analysis. This is only useful in boundary dominated flow, so infinite acting flow. These equations and relationships won't work in that case. It will only work if the system's already in boundary dominated flow. All right, so to do these Arps relationships, the only two equations you need are these two here. So D is for the nominal decline rate, and it's defined as the fractional change in flow divided by the change in time. So by fractional change in flow, that means the change in flow over the total flow, right? So it's a fractional change. So that's pretty simple. And the other equation is as such, where you take your nominal decline rate and you equate it to K, which is some constant, times Q, which is your current flow rate, to the power of B, right? And so B is a pretty important term on itself because it generally takes a value between 0 and 1, including 0 and 1. It can be greater than 1, but that's more of a special case, and that's not what this video is about. So if B in this equation here is equal to 0, then D will be constant and it will be equal to K. And the reason why is because Q to 0 is equal to 1. And so K times 1 is K, so D is equal to K. And that type of decline behavior is classified as exponential. So if B is equal to 0, then you have an exponential relationship. So if B is equal to 1, then D is proportional to Q with respect to the coefficient K, and its behavior is classified as harmonic. So these are the two extreme cases. B is equal to 0, B is equal to 1. Okay, now if you have B equal to any value between 0 and 1, then you have the intermediate behavior, and that's classified as hyperbolic. Okay, so in section 1, we're going to first look at exponential flow rate, and that's when B is equal to 0. So we take our equation we defined up here as the nominal decline rate is equal to the fractional change in flow rate over time, right? And all we're going to do is turn this into a differential form. So delta Q becomes dQ and delta T becomes dt. And we take this Q on the bottom and we move it out to the front. So then we have dQ over dt, and we move the Q out, and so 1 over Q, right? So that's the form of the equation that we're going to integrate. In order to integrate it, we're going to take this dt, we're going to move it up to this side, like as such as here. Now, at time equals 0, the flow rate is equal to Qi, and at time is equal to T, the flow rate is equal to Q. And so those are the limits of integration. And all you do is integrate that. On this side, it's pretty simple. dt becomes T, right? And the lower limit is 0, so it's just this. And this side, you get ln Q, and then you put the limits in and you subtract them from each other, so then you'll get ln Q minus ln Qi. And then what you want to do next is solve for Q. In order to do that, you combine these two because it's a logarithm minus another logarithm. You can take this one that's being subtracted and put it on the bottom of this one to combine them. And then you want to take the you want to raise both sides. You want to take the exponent of both sides such that you get e to the minus dt on this side. And if you go e to the ln q over qi, then because those are inverse functions, they cancel out, and then you just get the equation in this form. then multiply both sides by qi, and you get your flow rate equation for exponential flow. So this relates q and time. So if we wanted to graph this as a straight line, we could do that. If you notice, we take the logarithm of both sides, and we get log q. You take the logarithm of this side, and you'll get log qi e to the minus dt. You can separate these two, so you'll have log qi plus log of e to the minus dt. So here's the log qi, but log e to the minus dt is again log of an exponential function is an inverse function, so then it just becomes what's in the exponent, which is the minus dt. All right, so if you look at this equation, right, if you plot log q versus time, you should get a straight line with a slope of minus d. So maybe something like this. Okay, so here's your log q, here's your t, you get the slope minus d, right? So that's for the exponential relationship where you're plotting log q versus t. So this would be your production data versus time, right? Okay, so for exponential cumulative flow, how would you calculate that? Well, if you think about it, you just take your flow rate and you times it by the amount of time that it's been flowing for. That's if your flow rate was constant, but it's not constant. So you have to do it in the differential form and then take the integral to calculate the area underneath the curve. So we would want to consider how the flow rate changes between 0 and time t, the time of interest, and multiply that by dt. We'll substitute for q the equation we derived just a few moments ago, this equation here. We will substitute that into here, and when you do that, you get this equation. Now you just take the integral of that, which is pretty straightforward, and you get this equation here. Basically, it's just because it's an exponent, right? If you take the derivative of an exponent, you just bring the exponent, like the coefficient in the exponent down, and for integral, you would do the opposite, right? So that's why we get 1 over, or negative 1 over d, and then between the limits of 0 and time is equal to t, which is this here, if we write it out. So it's basically substituting for t equals t, which is this, minus t equals 0, which is this, and this is where t equals 0, and this is where t equals t. Basic calculus, right? And then what we're going to do is this is equal to 1, right? Because it's to the power of 0. That's why it disappears here. And this, if you look carefully, this q I e to the minus dt, this is equal to q as we have defined it up here. So we just substitute that back in, and we get the equation looking like this. We can simplify once more by combining the common denominator just to make it look more neat. And now you have a relationship for the for exponential cumulative flow. So this is the cumulative flow, like the total amount that has flown is related directly to the initial flow minus the initial flow rate minus the current flow rate divided by your nominal decline rate. All right, cool. So if you look at this equation carefully, what do you see? You see that Q, which is the cumulative total that you've flown, has a straight line relationship with Q, where the slope is negative 1 over d, and then you'd have an intercept here, which is qi over d. Like if you separated the qi and the q into two different over d fractions. But anyways, so it should produce a straight line where y is equal to x, right? And so that would look like this, where the slope is negative 1 over d. And this is for exponential cumulative flow. Okay, so that's the case where b is equal to 0. Now in the other extreme, where b is equal to 1, you have what is called harmonic flow. Taking the exact same two equations that we started the video with, which would be the fractional change in flow rate over the change in time, or in the differential form, it looks like this. And the reason why there's a negative there is just because if you go like q minus qi, right, you're going to get a negative number, just because qi will always be larger than q, right? Because qi is the largest q is ever going to get, and then over time, as time elapses, q gets smaller. So I believe that negative sign there is just to compensate for the fact that the number will be negative. All right, and so this is the same equation as we've defined before. So these are your two basic equations. So what are you going to do for harmonic? Well, what you're going to do is you're going to set b equal 1, and then you're going to arrange stuff, take an integral, and see what comes out. So first we want to consider the initial state of the system. That's where q is equal to qi. So if we made this equal to qi and d equal to di, right, so in this case your d will change over time, because it, as we described before, it's proportional to q with respect to the coefficient k. So it does change with time now. So you will have an initial di that is different than your later d. But if we only consider the initial conditions and we set b equal to 1, then we'll have di is equal to k times qi. Solving for k, which you do is divide both sides by qi. Then you get k is equal to di over qi. And then what we're doing here is we're taking this part of the first equation, the minus 1 over q dq dt, right, and we're putting it here. And since that's equal to d, and since d is also equal to k q to the power of 1, we can equate the two as such. And then since k is also equal to di over qi, we can substitute that into here, right? And when we do that, we'll get this is equal to this. Now we can rearrange that such that we bring the q, we collect the q's on one side, and then we bring the dt to the other side so we can do the integration. So we multiply both sides by dt, we'll get the dt here. We divide both sides by q. We'll bring the other q down here to get the q squared on the bottom. Now we just integrate that again through the same limits, 0 to t, qi to q. And when we do that, the left side is pretty simple. You get your t. And this side is also pretty simple, just basic calculus, right? Your 1 over q squared is just going to turn into a negative 1 over q, right, when you do the integral. So then you put your limits in, and because you had the negative sign here to begin with, the negative sign that's created by the integral is taken care of, and then you just get 1 over q minus 1 over qi, and then you solve for q. And to do that, you add this 1 over qi to both sides, and that looks like that. Then you flip, you can invert both sides by flipping the fractions on both sides, and you get q is equal to qi over dit plus 1. And that is your flow rate equation for the harmonic case, where you got flow rate versus time, and everything else is a constant or a known, because your initial conditions don't change, right? So di will only have one value and qi will only have one value because those are your initial conditions, and then q will depend on t in such a manner. Now, for this equation here, it's not like the previous ones where we can easily draw a straight line on either a Cartesian or a semi-log plot or log plot, because there's no simple Cartesian or semi-log relationship here. So we won't find anything like that for this particular case of the harmonic rate, flow rate versus time curve. So next we have harmonic cumulative flow. So just like before, we consider if q is constant, then to get the cumulative flow, you'd go the flow rate times time. But because flow rate changes with time, then you have to do the differential form and take the integral, just as before. This is the exact same as before up to this point. So we go cumulative flow is equal to the integral between time equals 0 to time equals t times q dt. Now we want to put an equation in here for q that's dependent on t, and we already have developed that just previously, which is this here. So we substitute this q and its representation into this q, and then you get this equation here. Now you just take the integral, which looks like this, just your basic calculus. I double checked this integral with computer algebra system, but then the result in the end is correct. But if you want to go ahead and do that calculus, go for it. But anyways, you could trust this is correct. And so what we have here is this equation that we developed before. We're just going to put this down here and then solve for what's on the bottom here by multiplying both sides by that, and then bringing the q down here by dividing both sides by that. And I believe what we do is substitute this into here such that we'll have a qi over q inside the logarithm, or it's written out here in full. So you have q is equal to qi over di logarithm of qi over q. And you can also split this up as before. So if there's a division inside a logarithm, you can take it out as a subtraction. So whatever's in the bottom gets subtracted, and you keep the coefficient in front of the logarithm. So basically I just rewrote q is equal to this here as a single statement. And then I suppose, rewrote it like this, which is just bringing them back together. You know, you might see it either way, but that's where those equations come from. So this was for a harmonic cumulative flow, right? So if you look carefully at this equation here, you have q, which is cumulative flow. This is a constant because this is all initial values. This is a constant, but this changes. So what would happen if you plotted this versus the logarithm of the flow rate? So cumulative flow versus the logarithm of the flow rate, well, it would be a straight line where this is y and this is x, or you could plot this as y, subtract this from both sides and divide this from both sides. And divide this from both sides, and then this would be your y and this would be your x, and that's what I've plotted here, and it'd still be a straight line, right? The only reason why I switch this around backwards is because in some textbooks it's shown more often like this, so I just want to be consistent with what you're probably seeing. But either way, it's going to be a straight line in this case. So far we've seen 3 straight lines, 2 for exponential and 1 for harmonic, okay? And those are the only straight lines, and I'm going to go over that at the end of the video to summarize, but I'm just showing you where they come from for now. So section 3 has to do with hyperbolic flow rate, and we use the exact same 2 equations. I don't understand why there's so many books with errors in them, and the internet with like big companies that try to describe the stuff and they'll have errors in them, or they don't have complete descriptions because, like, I don't know, it's just two equations and you just derive it. That's part of the reason why I made this video, just because I don't know, so many mistakes in those. Anyways, the last one, let's get to it. Section 3, hyperbolic flow rate. So if you got a b between 0 and 1, not including 0 and 1, obviously, because those are the two other cases. So like 0.5, 0.25, 0.75, 0.99, 0.0001, anything like that can be a hyperbolic flow rate, okay? So we start from the same equations as before. So we'll take this one, and as before, we'll do the initial state. So di, qi, okay? And then we rearrange this cell for k, just as before, right? And then it looks like what we're doing here is we're taking these two equations, this one here and this one here, and equating them. So we take KQB, and this one, negative 1 over q dq dt, when we equate them. And then we take what k is equal to and substitute it into k. And then we get this. And now we're going to rearrange it to do our integral just as before. So we times both sides by dt to get dt up on this side. And we also, one second here, dt, yeah, okay, we have to get the q onto this side because you need all the same variables on that side. So if we divide both sides by qb, then on the bottom you're going to have q times q to the power of b. Combining the exponents, you would have q to the power of 1 plus b, right? So you just take the integral of this by setting the limit between 0 and t, qi and q. And I just made it kind of more simple to think about by bringing this off the bottom by timesing the exponent by -1. And then I just did the integral on both sides, and you end up with something that looks like this. And then we want to solve for q. In order to do that, multiply both sides by b to get rid of it on this side. So that's why it's in front of the dit right here. Dit times b is b dit. And then all you have to do is add this to both sides. So because these have the same bottoms, then you're just going to have a +1 on the top there. So now you got something that looks like this, and then you want to just invert both sides, so flip them upside down so the fractions are the other way, and then take the b root of both sides, because that will get rid of the b, like q to the power of b. Take the b root on that side, take the b root on this side. That will get rid of the b exponent on the top, and then you'll just have the b root on the bottom for this part here. And then that's for your hyperbolic flow rate relationship, where you're comparing q flow rate with t time. Okay, so for the cumulative flow for hyperbolic, we're going to start with the same idea. We go, okay, cumulative flow, if q flow rate was constant, it would be just flow rate times time. But since it's not constant, then you have to do the differential form and take the integral, such as this. And now, just as before, the last two examples, we're just going to substitute this equation into here so that we can get it as a function of time, so we can do the time integral. So that's what this is. And then if you take the integral of this equation, you'll end up with something like this. Again, I double-checked this using a computer algebra system. If you want, you can do it by hand, but it's up to you, I guess. Okay, and now it's a very similar substitution as last time. We're just going to solve this equation, which is our equation we developed previously, this one, right? So that is the same as this equation. And all we're going to do is solve for this part of the equation on the left side. So to do that, we just multiply both sides by this, divide both sides by q, then put both sides to the power of b. That will get rid of this on this piece of the function, and it will add it onto the other side. So now that we have this in the form as it is, we can substitute this piece into here, because this and this are the same if you look carefully. So what does that do? That puts this piece here into here, and then you get a b into the exponent, and that's just going to multiply through. So this is going to be b minus b over b, which is just b minus 1, right? Because b over b is 1, and everything else stays the same. So here's some people just write the equation like this. Another way to write it is to write it as such as this, and in order to get to this form, you just see all you do is multiply the exponent by -1, and that will flip this one into this space, and then it looks like this. Sometimes it's written like this, and I just wrote it like this to show you how to get that version of it. And then another version is this one, and all they did here, I believe, was take out q to the b minus 1. So they divided this piece here by q to the b minus 1, and that would result in this, I believe. So, or qi to the b minus 1. So if you divide it by that, then that gets rid of this top q here. It puts this one here, because 1 divided by that is just going to be 1 divided by q to the qi to the b minus 1 is the same as qi to the 1 minus b, because you just put a negative into it, and then you can put it on the top. And then you would put it out here, so it would be q times qi times, sorry, every time I've been saying q, I meant qi, but I don't know, it's just like so many letters. Hopefully you understand what's going on here, but so you'd be qi, like qi times q to the b minus 1, so then it would be qi to the 1 plus b minus 1, and the 1 and minus 1 would cancel out, and then you just get qi to the b. So I don't know, hopefully that's straightforward, and I didn't even need to explain it. I'm just trying to go in detail here. Okay, so hyperbolic forms. Okay, yeah, so the hyperbolic, like in your Cartesian or your log plots, it's not going to make any kind of straight lines, not in any easy way. So what we have in summary here then is, from everything we've talked about, there's the two extreme cases where b is equal to 0 for exponential, okay, and b is equal to 1 for harmonic. So if b is equal to 0, you have exponential, and if you plot log q versus t, then you get a straight line. If you plot log q versus t for harmonic, where b is equal to 1, or for hyperbolic, where like b is equal to anything like 0.05, you're not going to get a straight line. You're only going to get the straight line in the if you have b equal 0. Same for if you plot flow rate versus cumulative flow. You're only going to get a straight line if b equals 0 or you have the exponential case. So these two, if you see a straight line when you plot those things, then you know you got an exponential relationship. For harmonic, that's where b equals 1. You'll get a straight line if you plot the log of q, or log of flow rate, versus the log of cumulative flow. If you get a straight line, then you have a harmonic. So basically, you make these three graphs, and if any of them give you a straight line, then you know if it's one of these two, it's exponential, and b equals 0. If it's this one, then b equals 1, and you got a harmonic. If you plot these three graphs, and none of them are a straight line, then you have hyperbolic. That's how you could tell which one you have. All right. Well, that's all for the video today. I hope that was helpful. Just putting this video together reminded me how confusing these things can be, because pretty much every source I looked at had either a mistake or it didn't have a full derivation, or something was missing or not explained well, or just confusing. I really hope this video doesn't have any mistakes in it, but if it does, I guess I just continue the trend. Write in the comments below and tell me what it was, and then hopefully people will see it. But I believe this is correct how I've described it. And I hope this helps. All right, cool. Thanks so much for watching my video, and have a good day. Bye.